Recall the reduction example. The work is linear and the number of transfers is at least n over L. Now let's analyze a concrete algorithm to see whether or not we can achieve this lower bound. Now here's the natural thing you would write in the conventional RAM model, that is the one without the fast memory. It maintains an accumulator S and makes a sweep over all the elements, accumulating them. Now you need to modify this procedure to think about when to move data between slow and fast memory. Now the variable S is easy. You can just assume that it starts locally in the fast memory. It's the same way you might treat any temporary scalar local variable in your favorite imperative programming language. For my pseudocode, I've just declared S to be local. Now I'm doing that just to be clear. Most of the time you can ignore these kinds of local variables. Now what about the array X? For simplicity, let's assume that little n is much bigger than the size of fast memory. Let's further assume that X is aligned on an L-word boundary. With these assumptions, let's transform the program to make slow and fast memory transfers explicit. Yikes! Let's start with the outer loop. As with the original algorithm, it steps through the elements of the array, but it does so one block of size L at a time. Next, there's the computation L hat. This mumbo-jumbo just determines whether the block that starts at position I is of length L or a little bit smaller. It's a detail, I just wanted to be clear, but most of the time we'll ignore this sort of detail. Next, there's the assignment to little y. This is an explicit load or read from slow memory to fast memory. Notice that it requests at most L words, which is one block transfer. Now since little y and s are both local to fast memory, the processor can execute this innermost loop. So what's the work and the number of transfers for this algorithm? The work is just the same as the conventional algorithm in the RAM model. That is, it's just theta of n. Here's the number of transfers. It's just the ceiling of n over L. Hopefully you can see how this falls out very naturally from the structure of the code. So how do these compare to the lower bounds? Why, they compare very well indeed. Before moving on, I want to make two remarks about what you've just done. First, I realize there was a lot of painful detail to do what must seem like a really simple analysis. We will make simplifications as we go, but I wanted to start by just being clear about exactly what has to happen under the hood in this model. Now my second remark. Yes, I know about caches. They're those fast memory thingies that the hardware manages automatically. In fact, there's an awesome OMSCS class that covers their design in a lot of detail. And while caches are very useful, what you'll eventually see is that they aren't sufficient to guarantee high performance. That is why we're discussing an explicit model of locality like this one.